Good morning. Any questions or comments? So I want to talk about, previously we talked about classical diffusion. I want to make it a little bit quantum, and the way we say this is like, we'll talk about semi-classical diffusion. Actually, all physics students know semi-classical approach a little bit. Maybe I can remind you quickly what that is. First, I think the starting example is like Bohr model, which is the way we find energy eigenstates of like hydrogenic atom without solving the Schrödinger equation, and it is like vastly underrated. People generally look down on this. I'm not sure why, but I think one of my favorite quotes is due to Einstein. He said for this approach, the highest form of musicality in the sphere of thought for semi-classical approach. So this is like hydrogen atom. Basically, you solve quantum problem without using quantum mechanics. And the second one is it's called the Haas 1-alpha effect. And there, like we first solve the we first solve the Schrödinger equation and find the energy dispersion, and we put the energy dispersion in the equations of motions, and we use Bohr-Sommerfeld quantization around the Fermi surface, right? You know that, right? She showed that to you. Mm-hmm. And then from there you can see like oscillations of all observables with magnetic field. This is what we call like quantum oscillations. And today we are going to do something like that. I mean, in the spirit similar, but I think technically that looks quite different. And what we are going to assume is, so suppose we have like some impurities, one here, one there, and the electron propagates from impurities to impurities, and typically what we need to have to be able to talk about like an electron at all, like an electron wave packet, we need to have like, okay, this is like some characteristic distance L, and L should be much larger than Fermi wavelength. Otherwise, right, we cannot talk about like an electron wave packet. And this means, okay, K Fermi is something like 1 over lambda Fermi. Using this, in this limit, K Fermi times L is much bigger than 1, or 1 over K Fermi times L is the small parameter of the problem. And when we have like a small parameter, that's a good thing because we can expand things on that. And that's the semi-classical limit. Just a short note, if you are familiar with a little bit field theory, in quantum mechanics, semi-classical limit is generally taken as h bar goes to 0. Okay. So this is exactly the same limit. Let me show you that. So h bar K Fermi is momentum, which is m v Fermi. Then K Fermi is equal to m v Fermi divided by h bar. And this thing, 1 over K Fermi, is 1 over K Fermi times L is equal to h bar over m v Fermi times L. And when this thing goes to 0, it means h bar goes to 0. So the same thing if you have ever seen something like that, the same thing we use field theory can be also generalized to here. So our goal here is add quantum mechanics to diffusion. And if you remember from last week, we have in quantum mechanics a wave function and a phase which is coherent, and in diffusion we have random walk and no memory. So we have to fix these two things. And to make the connection, like I will start with like a wave function, and the wave function is d to the r times psi squared is equal to 1. So this is like a probability amplitude, and we are going to try to pursue a strategy to relate psi squared to p of rt. So, and this is a diffusion we found last week. So let's take the Fourier transform. Rho of q of this is going to be d of r e to the minus I q dot r times psi squared. And we need to show the similarity of at least this quantity to diffusion. So what I will do is like first, okay, I'll do it in 3 stages. First, put particle at r is equal to 0 at t is equal to 0. So we have some particle at r is equal to 0, and this is t is equal to 0, and this particle is going to propagate in time, I don't know, something like that. And just to make sure that so this means the particle is like there's maybe some impurity here, some impurity here, impurity there, impurity here, impurity here, and like by bumping around impurities, I'm trying to imagine these to be straight lines, but like this process is happening so many times, it looks like a curved path. Therefore, to capture that, I'm going to evolve in time based on Schrödinger equation.
The previous equation just seems like a trivial result of Bloch theorem.
So this is not yet, right? This Q is not Bloch vector. We are like saying that any quantity can be Fourier transformed, right? And we are saying that take psi squared, which is like kind of like a density, and Fourier transform it, right? And lastly, in step 3, measure amplitude at r not is equal to 0 and at some time. So this is this can be expressed using like an equation. We start at r is equal to 0. We do some time evolution, IHT. I think everybody knows this, right? By acting with this operator, you can just evolve in time. And after a time t, you look at the projection at r vector, right? And this is, by definition, this psi of r comma t. And this is exactly what Feynman formulated quantum mechanics. Right? Before Feynman, people had like this like Schrödinger approach or like Heisenberg approach, and then later Dirac came and showed them to be identical, and people utilized that formalism for like 10-20 years. And in 1950s, Feynman like said like, okay, we can actually formulate the quantum mechanics in terms of classical paths, but what you need to do is you need to sum over all classical paths. And he introduced so-called like path integrals. So this is something like that, x of t, e to d. So this is like an exact relation. Let me first write and then explain. I over h bar. So what you need to do is like you need to decompose this h to many smaller h's, like by using like smaller times delta t. This is something called Trotter expansion, and in between you insert like identities in momentum space or like real space, and there are like many integrals, and these integrals can be taken because most of them are Gaussian. At the end you have like this wave function amplitude, and this becomes like a path integral, and in the path integral you have this action x of x t prime, and you start with Hamiltonian, and the action turns out to be, does anybody know what s will come out? Anybody showed you any path integrals? Yeah, I think we are not going to use it, but just for your general knowledge, I can tell you what it is. It's going to be Lagrangian. X is going to be t prime. Write it like this, following Gerwin and Young. So this is dt prime Lagrangian x dot. So this is like an exact operation. We will not use it, so I'm not showing it, but at some point if you need to do it, it can be done. It is not terribly hard. And the classical path is going to be extremization of this s with respect to these different paths. And if you do this, you are going to find Euler-Lagrange, right? Uh-huh. So inside H there is like p squared over 2m, right? Operator p, and there is like some v of x. And you need to act this on every single delta t, right? There is like e to the minus I over h bar, h delta t, and you need to have many of these like that. And you say when delta t, normally x and p and x they do not commute, so you can separate this h to p part and x part. But when this delta t is small, you can separate, and there will be like a p piece and then an x piece, and for each piece you can insert these identities either in like the p pp, or you can do exactly the same thing, dx xx, and those integrals turn into like c numbers, and you can take those integrals. It's like very tedious process, but like it is like very standard. There is no trick. And once you take the integrals, you start like, I think the amazing thing is like you start with Hamiltonian and you end up with Lagrangian, and then that's why we generally formulate field theory in Lagrangian. Of course, it also has like other benefits, like Lagrangian is invariant, but let's not get into that because none of this we need. I mean, just keep in mind, if you need this, you can learn it, but we can relate all of these things in terms of like a very systematic mathematical formulation. So without impurities, particles just go in like straight lines, right? And V is going to be just R over T. But with impurities, take all paths that connect. This one, maybe some crazy one, maybe one like that crosses itself like this. These are all allowed classically. Maybe it crosses and crosses and crosses, like all kind of crazy things you can imagine. They are going to be inside the amplitude, but not all of them have the same probability, right? Because we can write psi of r comma t as some normalization constant, 1 over z, I will use it. And this is j is equal to 1 to some n typically goes to infinity, right? There are infinitely many paths, but imagine there's like a finite one, and it will depend on time and final location. So this is r, this is 0. And we are going to have these phases, e to the I, theta of j. Of course, it is going to depend on r and t, but let me not write it at the moment. So this s, this is s of x j over h bar. Then we need so wave function is not observable, but the modulus of wave function is observable, and it is related to the density. So let me take the absolute value, and inside this it's going to be 1 over z I and j e to the I theta I minus theta j, right? I take the complex conjugate of one of them, that's why there's like a minus sign here. And what we need to do, like we did in the Anderson model, right? So this is going to be like a disorder specific quantity, right? A given disorder may change from another given disorder. So what we need to do is we need to disorder average this entire quantity. I think hopefully you remember how to do that. We just generate many disorders and we average like this. So this bracket is going to be disorder average. And here what we are saying is like that different paths cancel because of these phase fluctuations, right? Phases can go plus and minus erratically. So when you average over different disorders, they are going to average themselves out. And the only contribution here is going to be from I is equal to j part. And if I is equal to j, right, this is going to be e to the I 0, 1. And there are like n of these. It is going, okay, this is z squared, this is z squared. So this is going to be 1 over z squared n of r comma t. Is that clear? But here is the point we are using the classical limit. In the classical limit, this quantity should correspond to something we know, right? And what we know about this propagation is diffusion, right? The classical limit of this awkward quantity should be diffusion. Then this should be equal to p of r comma t, which was equal to 1 over 4 pi dt to the d e to the minus r squared over 4 dt. So this is the one we tried last time. But so far it seems like we are saying that quantum mechanics does not add anything. But we know, from the beginning, it has to add something, right? Because like there's like interference, and we have to single out a very specific scenario that this interference is very important. And for that one, let us consider return paths. Basically, right, if I take r is equal to 0, I'm going to be starting from here. I'll do many impurity scatterings and I'll come back to here. So there are like all of these are, maybe there's one impurity here, another one, another one, another one. Something like that. But for every path like this, like there is another path that is like time reversal partner of this path. So this is, let me call this path x of t. And because there is like time reversal invariance in my problem from the beginning, that's what I assume. If I reverse the arrows, this is also an allowed path. Right, I just will show this with x. Let me write it like tr of t. So if x of t is allowed, inside this sum, time reversal is also allowed. But the problem with these two paths, right, they are doing exactly the same thing. They are going to interfere destructively, constructively, right, because they have exactly the same phase. They are going to accumulate here, and there will be like additional probability to return to origin, because if you have the same phase, the waves here are going to, maybe I can use it like this. So I have some wave here going on, and this thing is going exactly the same thing, but opposite, right? Same wavelength, same number of like oscillations, and when they come back to origin, they should interfere constructively. And if they interfere constructively, that means like increased probability to be at the origin, and that means if the phase coming from this is e to the I theta, this is also going to be e to the I theta. They are going to have exactly the same amplitude, otherwise they would not be time reversal partners of each other. Therefore, we need to look at this thing. Psi at 0 of t is equal to 1 over z. I is equal to 1. Half of the paths are like written like e to the I theta. Let me use j here, j. And the second half is exactly the same thing, because they are the time reversal partners. Okay? And this is going to give me 1 over z 2 times j is equal to 1 n over 2 e to the I theta j. So this is the important factor of 2 that will make all the difference. So for this thing, factor of 2 enhancement to return to origin. Now I am going to take the absolute value and disorder average. So this is psi of 0 t squared and disorder average. So this is going to be 1 over z squared. This is going to be 2 squared is 4. But for the case n, we had, right, when you disorder average, we had n. The same argument runs for this, but the number of paths is not n over 2, so this is going to be n over 2. And this is equal to, okay, this is n of r comma t. Then this is going to be 2 times, right? This is 2, 1 over z squared n over n of r comma t. But we call this thing, this is 0 of t, but we call this one diffusion. Then this is also going to be the diffusion, right? P of t. What we are saying here is this is going to be, and we know the form of this. This is going to be 1 over 4 pi dt to the power d. So the picture is something like that. Initially, so this is R, this is P. Initially we were saying that here is the diffusion, right? This is like a Gaussian. that decays, and the typical distance here is something like 2 dt. But now the amplitude here is not 1, right? Because of these quantum corrections, the amplitude in the beginning is like enhanced. That's why we need to modify this diffusion. Maybe I can use something like that. So this is quantum correction. So this piece is classical diffusion. And if we have like an enhanced probability to be at the origin, that means a reduced probability to be transported. And if the probability to be transported is reduced, that means conductivity should decrease. So the correction to conductivity is negative because of this interference effect. So that means reduced conductivity sigma. So we can also formulate the same thing in the momentum space, right? In the momentum space, so the path k, you start with k, you scatter to some k1, you scatter to some k2, dot dot dot, and eventually you go to minus k. And this thing is exactly the same amplitude with starting with k, going to, okay, let me try to show the picture here. So this is k, so this is, I want to go to minus k, and I do it in many steps, but for demonstration purposes I'm only going to choose 2. So this is k1, k2, and I can take the time reversals of this and this one. This is minus k1, this is minus k2. So going in a path like this is the path, and going like this is going to be time reversal of this. So this is minus k2 and goes to minus k1 and goes to minus k. These are like the same amplitudes by time reversal symmetry, and if they are the same amplitude, they interfere constructively, and if they interfere constructively, this process is enhanced, and this is what we call enhanced backscattering. So this is actually something called like a glory effect. I mean, in the case of quantum, it is quite novel, but it actually happens every day. So this is called, for like light is a wave, and it also shows this. Maybe I can quickly try to show you what this glory effect is. This is like a descending airplane, and as the airplane comes, okay, maybe I can take it back a little bit. So the sun is right behind the airplane, and you are looking down the clouds, but there is like one spot in the clouds where the scattering back to you is like enhanced, and you can see there's like some like these rainbows, but if you come a little bit close, you start to see, maybe I ask, do you know what that is? This dark shade, could anybody see it? It's the plane, right? And it is the shadow of the plane, because light is coming from sun going through airplane, but airplane is the shadow, right? There's no light coming from airplane, so there's like a shadow here. So you can see all the scattering from this small region is like enhanced. And the width of this little window here is like this delta, let me call this delta theta. The angular and angular window of this enhancement is going to be proportional to wavelength divided by L. But in our case, wavelength is like Fermi wavelength, L is mean free path, and it's going to be 1 over k Fermi L, which is a small interval. So maybe before I finish, I want to mention something called echo currents. Echo currents. So this Gloria effect we have seen is like classical waves, right? Classical waves also interfere, and we can see it with our eyes. But in the case of electrons, we have wave function, an unobservable wave, right? Psi cannot be observed, but still they are going to display the same effect, and this effect is generally referred to as echo current. And let me explain what this is in like 5 or 10 minutes. So I want to consider an electric field. Before echo current, let me consider like a Fourier mode of an electric field. Like let's consider like some E of t is equal to some constant times e to the minus I omega t. And Newton's laws are going to be m v dot of t is going to be minus e of t minus m over tau. And this is the drag force. I think we studied with this previously. I'm going to substitute v of t is equal to some v times e to the minus I omega t. Let me substitute this. So this is going to be minus I omega m v e to the minus I omega t is equal to minus e0 e to the minus I omega t minus m over tau v e to the minus I omega t. Now I can cancel these. Thank you. And I'll divide by m and erase this and erase this. And I'll take 1 over tau to other side. So 1 over tau minus I omega times v is equal to minus e over m e0. Then which gives me v is equal to minus e over m 1 over, actually let me take tau to here, 1 minus I omega tau times e0. And from here j is equal to minus e m v, and this is going to be this thing times e squared. Then the frequency dependent conductivity sigma of omega is going to be this piece, right?
I think we should multiply that.
Oh, there is also n. Yes, thank you. Yes, absolutely. So this is n tau. So here maybe I can ask you 2 questions and you can think about this. As so it seems like as omega goes to infinity, what happens as omega goes to infinity? So this term will dominate, right? This term will dominate and tau will cancel, so no tau dependence. So that is a question for you. Why? Yes?
I mean, this is a complex number. If
Yes.
it goes to infinity, I mean, we can compare any complex number.
Exactly. There's also like second thing. So first thing is like first there seems to maybe I can ask your question first and then this one. First, it is like sigma is complex. What does it mean? So you need to think about this. What does like a so like right there's like electric field. It has some phase.
Attenuation.
Huh?
Attenuation.
It is simpler than that. We are not thinking about attenuation here. We are just like these things are phases, right? And if you multiply something with I, it changes its phase, right? So there's like something about that. And the second thing is like if omega is like if the electric field is oscillating infinitely fast, it seems like tau dependence drops out. Why is that? Right? So just think about that. So this is you want homework.
As omega goes infinity, the conductivity is going to be just measured part. So
Yes.
tau's are going to cancel out.
Not imaginary sigma is perfectly meaningful. Like, right? There is no problem with that.
Tau's just cancel out.
Yes.
Are you trying to say find the physical dependence?
Yes. Not the physical dependence. The result is here.
Yeah.
How do we make sense of this? What is the meaning of these things? There is like a physical meaning. It's not complicated. It just takes a little bit of thinking, but I don't want to give it to you. Both of these things are meaningful, and the result that tau independence in infinite frequency is also meaningful. Now I want to think about a pulse electric field. Now consider pulse E of t is equal to something like E naught of delta t. I just turn on and off electric field. And from here I can calculate J of t. And it is going to be d omega over 2 pi minus infinity to infinity. I'll sum all Fourier components, e to the minus I omega, e squared n tau over m, and conductivity we just found 1 minus I omega tau times E naught. And this integral can be taken, right? This is a second homework. Take, how many people know contour integrals here? I think everybody knows, right? There's only one contour integral. You just need to choose which way to close the contour, and for that you need to look at the exponential. Take integral using complex contour integral. And the result is, let me give you the result. The result is something like this: e squared n over m. So this is E0 e to the minus t over tau times theta of t. And pictorially, what this means is, so this one is J, this one is, let me draw the I, this one is T. So this thing starts at 0 and decays exponentially like this. So this is, right, if you like turn on electric field and turn it off immediately, there will be some current flowing through the sample, but it is going to decay exponentially, and decay rate is going to be proportional to this 1 over tau. But from here, from the quantum correction, right, exactly like this glory effect, I mean, most classical transport is going to be in the direction what you expect, but there will be like a small tiny part that is in the opposite direction. And this opposite direction is what we call echo currents. So and the echo current, because we said it is proportional to diffusion, and diffusion return probability in the diffusion, and it is going to be 1 over 4 pi dt to the d. So this current is proportional to 1 over t to the power d over 2. Right? I'm just writing this. Where this one is exponentially decaying. This one is power law decay. And in the long time, if you integrate over all these possible times, this is going to diverge, right? And there will be like an enhanced probability to return. So maybe I can just, so this echo current is going to be our like first, it's not actually, previously we have seen many like signals of localization, but this is the first series signal of electron localization due to impurities or disorder. And if we integrate this thing over all times, this is going to blow up. So echo goes to infinity if d is less than or equal to 2. And this is going to be, in the second hour, I'll spend a little bit more time to see that, show you that actually all states are localized in 1 and 2 dimension. Whereas in 3 dimension, it's not localized. But if you increase the disorder strength, you can do phase transition from delocalized to localized regime.